In this video, we're talking about logistic regression in multidimensional case, and we'll also discuss interesting concept of decision boundary. Let us recall what we talked about logistic regression in one-dimensional case. We use sigmoid function depending on weight W and bias B, and this is how this sigmoid function looks like. And also we got the expressions for the update of parameters W and B by gradient descent method. In multidimensional case, everything remains intact. Everything remains in the same way, with the exception that instead of just product of W and X, we're using a dot product of vector W and vector X. Now they are vectors of dimension n. So, and we have the cost function, which looks almost like also in one-dimensional case, but we now use the dot products for its calculation. So, and we can obtain the iterative equations to find the optimal vector of coefficients, weight coefficients W and bias B. These are at the bottom part of this slide. So, let's consider an example, but before the example, we will consider the decision boundary. Decision boundary, what does it mean? Decision boundary means some curve or plane, it depends on how many dimensions do we consider, where the sigmoid function takes the intermediate value of 0.5. 0.5 means that below it we classify our samples as y equal to label y equal to 0, negative decision, and if the value of sigmoid function is above 0.5, we classify it as positive, y equal to 1. So due to the definition of sigmoid function, this just corresponds to the following equation. Dot product of W and X plus B is equal to 0. B is a scalar. In this case, this is a scalar. I have showed it in bold, but it should be corrected. Yes, B is a scalar value. So dot product W and X plus B equals to 0. This is a decision boundary. Let's consider an example. Here we have a set of points which we want to classify. 0 points are initially labeled with labels 0, and the red points are labeled with label 1. So we will apply the gradient descent method. I will run the corresponding Python code, and we'll see what we obtain. So these are our points, which are just have shown on this slide, and we run the gradient descent method. This is a convergence of cost function decreases. Also, we could take more iterations, more than 2000, but nevertheless, we obtain the coefficients W and B and the corresponding decision boundary, which looks like this. So the coefficients of the weight coefficients are 1 and 0.969, and the bias is minus 0.968. So we have the equation for this line, for this line, which serves as decision boundary. So I think it's quite clear. Let's consider another example, more interesting example. Just a moment, I will run another set of points. Yes. In this case, these are points which fill some kind of round or ellipse. Blue points are points with label 0, negative decision, and points with label 1 are red points, positive decision. So we'll try to find to find the decision boundary in this case, but of course we should observe that it will not be linear, of course, in this case. We will use squared features, x1 and x2 as squared features. And in this case, I will show it for this example here. So the corresponding, if we use squared features, the corresponding equation for the decision boundary will be as follows. Scalar product of vector w and squared features, vector of squared features plus bias b equals to 0. So let's look how we proceed in this case. Did I run the program? Yes, it's here. Okay, let's continue. Let's continue. Let's find which coefficients were found by. So the following decision boundary. And you can see here at the bottom the equation for the corresponding ellipse. It's almost a circle. X squared plus y squared equals to 0.96. So this is just scaling of Python. So we see it as ellipse, but we can see how a proper decision boundary was formed. Yes, this elliptic form of decision boundary was found by the algorithm. Let's also look what were the estimation error. 1%, approximately 1% of error was the classification error. Yes, probably somewhere one blue point got outside this decision boundary. So it shows how this algorithm works. Again, we have this graph of cost function by the gradient descent method. Okay, if we just continue, we can also see the ROC curve of dependence of precision from recall, which we considered in our previous video. Yes, in this case, almost perfect classification, and we have area under the curve equal to 1. Let's come back to our slide. So we have shown how to find decision boundary. Decision boundary, we just run gradient descent method, find appropriate coefficients w and b, and then we can construct decision boundary as is shown on this slide. Thank you very much for your kind attention.